Magnetism. That's what we're going to talk about today.
Where does Santa Claus like to vacation? Antarctica. After spending so much time up north, he has an attraction for the South Pole. It is a very complex process overall, but the simplified version of this is that there's a solid iron nickel core with a liquid iron nickel core surrounding it. That liquid core moves with convection currents, creating an electrical movement of charge throughout the core of the Earth. This creates a magnetic field. True north is about the axis on which the Earth rotates. Magnetic north is about 11 degrees off from that, based upon the convection currents created by the inner core of the Earth. To build a compass, you can actually take a needle and magnetize it, float it on top of water, for example, taking a sewing needle that's magnetized and putting it onto a cork and floating it on some water. This will point towards magnetic north. Remember that magnetic north, the direction that the needle is pointing in, is actually the south pole of the Earth as a magnet.
How do compasses work? Compasses have helped lost souls find their way home for more than 2,000 years. But how does a little metal needle actually know which way is north? In a sense, the Earth itself is a giant magnet. It has a north pole and a south pole, and those poles can interact with other magnets in the same way that the magnets on your refrigerator can. Opposite poles attract, while like poles repel. The needle in your compass is also a tiny magnet, made from magnetic rock like iron and suspended in liquid so that it can swivel freely. And so, when you hold your compass level, the north pole of the needle naturally aligns with the opposite pole of the Earth's magnetic field, a spot on the top of the globe that we call magnetic north. Unfortunately, for some explorers, Earth's magnetic north pole doesn't exactly align with the geographic north pole, otherwise known as true north. While true north always sits at the top of the Earth's axis in the middle of the Arctic Ocean, the magnetic north pole is about 1,000 miles south in Canada. To make things even more complicated, magnetic north has an annoying habit of moving around as our planet's magnetic field warps over time. By some estimates, the magnetic North Pole has moved more than 600 miles towards Siberia in the last 100 years. It may not be 100% accurate, but the swiveling little magnet in your compass is still a pretty reliable bet for finding your way home. How compasses work? Just another one of life's little mysteries. Want more Life's Little Mysteries? Check out these videos and read more at livescience.com.
Does a magnet have to possess a north pole and a south pole? Absolutely. You have to have one with the other. They can't be separated.
One example of a non-contact force are magnetic forces. Here we've got a big chunk of magnets and a small stirring rod, which is also a magnetic stir bar. We'll actually put them in close proximity, but not touching, so they will not be in contact. Let's see what happens. All right, see if it jumps up again. Indeed, when it gets close enough, you will actually have a non-contact attraction where the magnetic force overcomes a gravitational force. Very cool science.
Opposites attract. Poles that are similar repel each other.
All right. Opposites attract. That's true for magnets. So we'll see what happens if we get two ends that are the same, such as two south poles or two north poles, and put them together. Jumped up. You can actually flip them over, try the same thing. Again, opposites attract, but like poles will actually repel. Try to put these two together, they're repelling each other. It's really hard trying to push them right together. Well, let me see if I can squeeze them really tightly and hold them in place. Then I'm going to let them go. It jumped up and flipped over. That's because like poles repel each other. Very cool science.
Hans Christian Ørsted, while performing a demo, he found there was a relationship between electricity and magnetism. Andre Ampere, he found that two current-carrying wires actually have mutual attractive force between one another. The source of a magnetic field is moving charge. Likewise, the effect of a magnetic field is to apply force to moving charge. A permanent magnet is a ferromagnet that will actually retain its magnetic field after it's removed from an external magnetic field. That permanent magnet would be the kind of magnets that you use to put pictures on refrigerators. The right-hand rule, here's a video of it.
Hello everyone, and welcome to your video tutorial on the right-hand rule. And so, we have a couple right-hand rules. The first that I'm going to discuss deals with magnetic force on a traveling charge. Now, it's crucial that I say traveling charge because a charge that is stationary in a magnetic field will feel no force. So let's give this thing a velocity that is directed to the right. That is our velocity v. And let's say all around this point charge, I've got a force that is directed out of the page. Sometimes it's denoted circle dot, sometimes it's just dot. But just make sure you have your cutie shot and then you will be fine. Okay. So all around, magnetic field coming out of the page like this. Okay, so the right-hand rule to get the force on that charge, you run your fingers along the velocity, like so. Then you curl your fingers in the direction of the magnetic field. Well, how my fingers can curl right now is only in. If I turn my fingers like this, they can only curl up. I have to turn my hands sideways like this. Fingers are still pointing along the velocity. They can now curl out of the page, and I have a force that is directed down. That would be my magnetic force at that instant. Now, that force, by definition, is perpendicular to that velocity because magnetic force is a cross product of velocity and magnetic field. The magnetic force on a charge is QVB sine theta. Now in this case, the angle between magnetic field and velocity is 90 degrees. So sine of 90 is just 1. So because of that, the magnetic field can't do any work on this charge. It can change its direction, yes, but not its actual magnitude of velocity. So this thing would rotate around in a circle like so. Everywhere your velocity is tangent and your force, your magnetic force, is directed back in towards that center. It's the centripetal force. Now, if I make that a negative charge, you can still use the right-hand rule, but whatever you get, make the force the opposite. I always do positive for right hand, and then I do the same thing, but for the left hand if it's a negative charge. So if I made this negative, I take my left hand, fingers along velocity, curl in the direction of the field, and my force would be up. So that is the right-hand rule for a charge. Now, a current-carrying wire, let's say my current is running this way, and let's say again my force, my magnetic force is coming out of the board. Okay. I still do the right-hand rule, and it's really not all that different. The current is really kind of like the direction of the velocity. You run your fingers along the current, curl them in the direction of the field, and this wire would experience a force that is directed down. Now, that's force on a current-carrying wire, and the force on a wire is given to you as BIL sine theta. where sine theta is now the angle between the length of the wire, which is basically the wire, and the magnetic field. In this case, again, it's 90 degrees. So that right-hand rule, fingers along the current, curl in the direction of the field, thumb is the direction of the force. That's for force on a current carrying wire. But the last right-hand rule that we have is for finding out the direction of a magnetic field that the current carrying wire itself is creating. So here's my current. Let's just say that my current is running to the left. Here's how you figure out how this current is generating a magnetic field, because current generates a magnetic field, and magnetic field can generate a current. Okay? So here's how we figure out the direction of the magnetic field. Grab the wire so that your thumb points in the direction of that current. So I'm grabbing like so. As I'm grabbing, my fingers above the wire are going into the board, which means above this wire, I have magnetic field going in. As my fingers wrap around and they come out of the board below, which means below, it is generating a magnetic field out. So let's say that below this wire, you had another current carrying wire with current flowing in the opposite direction. Well, here's what's crazy. That top wire generates a magnetic field out. And the magnetic field that it generates exerts a force on this current carrying wire. So remember, move your fingers in the direction of the current. Curl them in the direction of the field, and that wire would experience a force that is directed down. Now, what about the top wire? This wire, the bottom wire, is also generating a magnetic field because of its current. Now, let me run and grab my blue marker really fast. Couldn't find it? So, here we go. Bottom wire. Grab it so that your thumb points in the direction of the current. Above this wire, it is generating a magnetic field out. So I will draw its field on that wire. Okay? If this is wire A, this is the magnetic field created by wire A. Below wire A, it's got a magnetic field going in. So that top wire, call it wire B. That top wire now has a magnetic field on it. So to figure out the direction of the force on this wire, fingers in the direction of the current, curl them in the direction of the field that's actually on the wire. Fingers curl out, thumb points up. That wire would experience a force that's directed up. Two wires, current in opposite directions, they repel each other. So hopefully that helps you out with your right-hand rules.
What are some units for the magnetic field? Tesla and Gauss. Here's some strengths of different magnets. What you'll find is that the Earth's magnetic field is pretty weak compared to that of even many permanent magnets, or especially the superconducting electromagnets, which can produce very high magnetic fields. Could you actually move a charged object with a large magnetic field? Possibly, but since the mass is so large, it's not really feasible. Typically, you will use magnetic fields to move things like protons, electrons, and ions, various anions and cations that you'd find. Those are the primary things that we move because they're much smaller, their mass is smaller, but their charge would be +1, +2, -1, -2, -3, etc. Illustration of a current carrying wire and its magnetic field. You can use the right-hand rule to figure out the magnetic field and the force of a current carrying wire. Illustration of a simplified electric motor. Another illustration of a simplified motor and the magnetic flux. More on a simplified electric motor.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions: a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC power sources. To know more about it, please check the next video. Thank you.
Here's an illustration of a uniform magnetic field. Path of charges in a uniform and non-uniform magnetic field. Ernest Lawrence won the Nobel Prize for his work on the cyclotron. He was able to figure out that the period and the actual speed of a particle are independent of one another. Donald Glaser won the Nobel Prize for his work on the bubble chamber, which was used to detect high-energy particles. In a mass spectrometer, you can actually measure the mass-to-charge ratio of different isotopes, molecular ions, or other ions that you have. You'll actually take your sample and heat it up, and it will either break apart into various ions or stay together as a molecular ion and be accelerated down a tube through a vacuum. Once it's moving fast enough, it will enter the magnetic field. Based upon its charge to mass ratio, the circular motion that it will go in will differ. So something that has got a heavier mass to charge ratio will actually be on the outside, versus something smaller will be on the inside. That's how a mass spectrometer works. A charged particle in a non-uniform magnetic field will have a trajectory that is very complicated. That's why they usually try to have a much more uniform type of magnetic field for it to move in. A magnetic mirror is a magnetic field in which charged particles that are moving towards it will be directed backwards in the direction that they came from. A magnetic bottle is devised so that there are two magnetic mirrors, and they will take charged particles and reflect them from one end to another. Most of the time, the charged particles will be in the center between the two mirrors, where the magnetic field is mostly uniform. They hope to be able to use this to be able to capture the charged particles in a fusion reaction. A magnetic bottle is hoped to one day be able to contain the plasma from a fusion reaction. The aurora borealis, or the northern lights, is this green glow that will occur near the poles. This is because of charged particles coming from the sun hit and are diverted around the earth because of the magnetic fields. Those magnetic fields will actually interact with the Van Allen belt to actually give this glow at these poles near the North Pole and the South Pole. Here's the Biot-Savart law. Historical figures Biot and Savart, they were able to use a magnetic needle from a compass and see the electrical current would influence that magnetic needle. Here's the magnetic field of a distribution of currents. There's an illustration plus the equation that goes along with it. Here's an illustration of circular current loops. The Biot-Savart laws can actually be modified to describe these as well. Here's an equation for a magnetic field in a loop of any shape. If you have currents from two wires, how would they interact? Well, if the currents are flowing in the same direction, the wires would be pulled and attracted towards one another. If current is flowing within two wires in the same direction, those parallel wires will be attracted to one another. If the currents are moving in opposite directions, the two wires that are parallel to one another will be repelled. There's actually a formal definition for an ampere. If you have two wires that are 1 centimeter apart, the force between them would be 2 times 10 to the negative fifth newtons per meter for the length of each wire. The definition of Coulomb is the amount of charge in a wire that passes a certain point every 1 second when 1 ampere is the current. A solenoid is a cylindrical magnetic coil that acts as a magnet as current is passed through the loops. These two equations describe the magnetic field of an ideal solenoid. Here's a comparison between an ideal solenoid and a real solenoid of finite length. A magnetic moment is a quantity representing both the magnetic strength and the orientation of a magnet or another object that has a magnetic field associated with it. Some examples of magnetic moments are loops with electrical current, permanent magnets, electromagnets, planets like Earth that have a magnetic field, or electrons with spin. The magnetic moment of an electron is caused by its intrinsic spin and charge that's associated with it. When I was first working at the University of Alabama, I actually learned to work with electron spin resonance, or EPR. That was a way to actually study the electron spin and its interaction with magnetic fields. It's very cool experiments that we did. Electron spin is a quantum property of the electron. It is related to its angular momentum, and this angular momentum is a permanent value. If you're going to magnetize a piece of iron with an electromagnet, you'll take the piece of iron and you'll stick it in the center of a big coil of wire, run electricity through it. That way you're creating a magnetic field. Since this material would have to be a ferromagnetic material, it would then maintain that magnetization even after the electrical current is removed and there's no more electromagnet. This is a permanent magnet. Illustration of magnetic moments inside a chunk of iron. Here are 3 equations that allow you to calculate magnetization of a material. What is the magnetic field of a cylindrical magnet compared with that of a solenoid of the same size? Well, it's actually going to be identical. The magnetic moments from electron spin end up being identical to what you would have for moving electrical charge. Here are 2 equations that allow you to approximate the magnetic field inside and outside long cylindrical magnets. These approximations are valid for very long cylindrical magnets that are not near the end of the poles. That means you're looking not right at the very ends of those magnets. These equations should hold true. How do you create an electromagnet? Well, you actually take a solenoid, a long coil of wire, and run electricity through it, but also have a material on the inside that can be magnetized, some type of ferromagnetic material such as iron. There are 3 types of magnetic materials. There are diamagnetic materials, paramagnetic materials, and ferromagnetic materials. Magnetic materials will actually have paired electrons, spin up and spin down. They will have a weak negative magnetic susceptibility. They will also, when you remove them from a magnetic field, they will not retain their magnetic properties. In a magnetic field, they will actually be weakly repelling to that magnetic field. A paramagnetic material is a material that actually has unpaired electrons. These unpaired electrons will give it its unique properties. They will actually have a weakly positive magnetic susceptibility. They'll be weakly attracted to a magnetic field, and when you remove a magnetic field from the paramagnetic material, the magnetic properties go away. Molecular oxygen will actually have unpaired electrons in it. This means that when you expose it to a magnetic field, it should interact and be magnetized just like some other paramagnetic materials.
Qu'est-ce que je raconte encore? C'est cool. C'est cool, hein? C'est cool. Je trouve que c'est un direct. On a assez d'oxygène? Ah non, encore beaucoup trop. Bien, je suis sûr que... C'est trop dingue.
A ferromagnetic material will also have unpaired electrons. However, it has a strong magnetic susceptibility that is positive. The magnetic susceptibility maintains there even after being exposed to a magnetic field. This would be the case of a permanent magnet such as iron being magnetized. The exchange force exists only in ferromagnetic materials. With the exchange force, ferromagnetic materials will have adjacent atoms interact with electrostatic repulsive forces to have an alignment of the material to align their magnetic fields. Ferromagnets have a critical temperature. This is the temperature that below the temperature they're a ferromagnetic material. Above that temperature they'll actually convert and be a paramagnetic material. So one of the things you have to do is make sure that the material is cooled low enough and it will become a ferromagnetic material. Things like iron, you don't have to worry about its temperature because its critical temperature is usually much above room temperature. But there are some special materials that can become ferromagnetic materials, but you've got to cool them down to very cold temperatures. Here's an illustration of magnetizing a ferromagnetic material.